So we're very welcome. So we're very happy to have Sacha Davidson today to give us a talk. So Sacha is an expert on flavor physics and has been working on many different topics, also axions and leptogenesis. But recently she focused a lot, I think, also on effective field theory and Lepton Flavour relation, charge Lepton Flavour relation, and neutrinos, and that's what she will be telling us about. So flavor changing non-standard neutrino interactions versus charge Lepton Flavour relation. And if you want to follow along the slides or want to look at the slides and go back, you can also download it from the website. It's up there. So please, Sacha.
So hello. I'm very happy to be talking to you because, like many people in my institution, we think there are all these interesting people in Australia, but Australia is so far away, we never interact. So maybe we can continue this kind of interaction even when travel becomes allowed again. However, this is the first time I give a seminar on the web, and I discovered there's a disadvantage to not traveling to give your seminar, which is that you don't have the trip to polish the talk. So I hope the talk's going to be okay anyway. This is work I did almost a year ago with Martin Gorban, so I've forgotten pieces of it. But what I wanted to talk about is contact interactions called non-standard neutrino interactions that one can try and look for in, for instance, neutrino oscillations, and their relation to charged Lepton Flavour violation. And in particular, to whether decorating the non-standard neutrino interactions with loops can allow to turn the neutrino legs into charged leptons and therefore generate a charged lepton flavor changing interaction. So did the slide change for you?
Now I did.
Aha, okay. So neutral current, non-standard neutrino. Is okay?
Yes, it's okay. So maybe other people should mute their microphone to avoid any feedback.
Yes, all right. Please mute the microphones. Otherwise, I will use my powers. Of course.
I forgot to say, if you have any questions during the talk, please just ask them, because I don't have a very good idea of who I'm speaking to. So you should tell me if I'm boring you or if I'm saying things that don't make sense. Anyway, so at the top of this slide, there is an example of a neutral current non-standard neutrino interaction. So as you see, it is a 4 fermion contact interaction that involves 2 neutrinos of either the same or different flavor. They're standard model active neutrinos, and they are talking to a current of 1st generation fermions. And the reason these things were introduced is that this could be new physics that you would find in neutrino oscillations. So the idea is that the neutrino oscillations give you a very clean probe of the little known neutrino propagator, because you have a macroscopic quantum mechanical process. And these non-standard neutral current non-standard neutrino interactions would contribute to the matter effect, to the neutrino mass matrix via the matter effect. So more or less like this. Now, in this talk, I'm going to be focused on the neutral current non-standard interactions. So these things that look like this. I should add that there are also charged current non-standard interactions that would, for instance, in a neutrino oscillation process, contribute either in the source or in the detector. And recently, people have considered something that are called GNI, which are still two other fermion interactions, but you allow for a light right-handed neutrino or sterile neutrino, and that allows you to construct different Lorentz structures in your four fermion operator, for instance, scalars and tensors, as opposed to having the vector-vector construction that you have in NSI. So I'm not going to be talking about that. I'm focused on these neutral current things. And I'm going to spend the rest of the talk essentially discussing this, the possible values for this epsilon thing. So if you're unfamiliar with epsilon, you might want to write it down on a piece of paper or something, what its definition is. I'm sorry, I can't write it on the blackboard for you, but that's a disadvantage of webinars. So the point is, it has two superscripts, which are the flavors of the two neutrinos. And in this talk, I'm going to be particularly interested in processes where the flavor of the neutrino changes. And then there's a subscript which tells you whether your external fermion is an electron, a down, or an up quark. Okay, so if you have such things, they obviously contribute in neutrino oscillations. So what's on this slide are some constraints on the possible value of epsilon that come from a paper by Concha Gonzalez Garcia and collaborators from a year or so ago. And I remind you, epsilon is a 3x3 matrix in flavor space, right? I'm assuming it's symmetric. And there are three matrices, one for up quarks, one for downs, and one for electrons, assuming a vector current on the external fermions. And so there are three possible entries of the three matrices are given in this plot. And you see that current oscillation data is sensitive to values of epsilon that are somewhere between 10 to the -1 and 10 to the -2 on the off diagonals. Okay. Now, these constraints are combined oscillation data with the coherent experiment, which helps constrain, for instance, a little bit on the diagonals. Okay. Now, you can therefore imagine that one of the things that Dune could do by having more precise measurements of neutrino oscillations is be sensitive to smaller values of epsilon. And there are various studies that explore how small Dune could see, but let's say of order 10 to the -3 in epsilon is something you could see in long baseline neutrino oscillation experiments. Let me also say that these are constraints. In other words, bigger values than this are supposed to be ruled out, but they assume that NSI are moving our small corrections to the standard model plus neutrino masses solution. In other words, if you've ever heard a talk by Yaseman Farzan on NSI, she has models with values of epsilon that are bigger than this. They don't reproduce the usual large mixing angle solution in the sun, but a slightly different one that is almost as equally good fit that's called the LMA dark. And I think it's in a different quadrant of the mixing angle space. Anyway, okay. Now, there are also constraints from neutral current neutrino scattering experiments. Most of these are quite old experiments like NUTEV or the original version of LSND. And you see those bounds are sort of an order of magnitude, tend to be an order of magnitude weaker than the ones from oscillations. Okay, now what you might think about NSI is that since the standard model neutrinos are in a doublet, you should be able to replace the neutrino by a charged lepton, and therefore you could constrain the coefficient of that contact interaction to be very small because we don't see flavor change in contact interactions involving charged leptons. So we can consider an example. Let's, instead of writing down those QED invariant contact interactions we were writing before, let's remember the standard model is SU2 invariant and write down all the possible operators that can change a tau neutrino into a mu neutrino on electrons. So there are three of them, and here they are. There is a triplet SU2 contraction like this, a singlet SU2, and a operator with the electrons are right-handed, okay? So I forgot to put, I mean, using notation that I forgot to define, L here is a doublet lepton and E is the singlet. I should have put projection operator, sorry. Now, if you put these operators into your Lagrangian, you discover that non-standard interactions are proportional to the sum of these two, or to that one. And tau to 3 leptons, in other words, tau to mu EE bar, will be proportional to the difference of these two. So it's clear that lepton flavor violation will impose constraints on the epsilons you can write down, but it doesn't mean that all of them have to be 0. In particular, as long as you set that one equal to that one, and this one to 0, you're doing fine at tree level. Now, there's another way to avoid lepton flavor violating constraints altogether, and that's to say, aha, but I will build my non-standard neutrino action at dimension 8. And I contract the lepton doublet with the Higgs doublet in such a way that when the Higgs gets a VEV, this picks out the neutrino. So now I have an interaction that has 6 legs, but that doesn't matter at low energy. I have NSI and no charged lepton flavor violation. The price you pay for doing that is now your little parameter epsilon is suppressed by the scale of the new physics that I'm calling lambda here to the 4 over the 1 over that scale times the Higgs VEV to the 4. And remember, we're looking for values of epsilon that are bigger than something like 10 to the, not 10 to the minus 2, but 10 to the minus 3. So your new physics scale seems to be quite low, and in particular, accessible to the LHC. So you might wonder, whether this is starting to become Baroque effective field theory, and you need to build a model. Now, let me make one comment that I forgot to make earlier. Non-standard neutrino interactions are contributing to oscillations via the matter effect, which is forward scattering. And forward scattering is, of course, at zero momentum transfer. So irrespective of how low you make the mass scale of the exchanged particle here, you will always have a contact interaction for NSI. You may not have a contact interaction in the neutrino scattering experiments. You would not have a contact interaction in, for instance, Lepton Flavour violation, but you do get one for NSI. So that, and the large size of epsilon motivates building models where the mediator is light. So this has been studied in quite some detail by Yaseman Farzan. There's also a paper by Pospelov and Pradle. And the idea is you put a light Z prime, you give it a mass that is somewhere above 10 MeVs to avoid any cosmological astrophysical problems. And then you give it a small coupling. And it's quite easy to put in such an relatively invisible Z prime if it has flavor diagonal couplings. There are also models where it has flavor changing couplings that have been, for instance, there's a recent model of Yaseman's. Now the other option is to consider heavy new physics and just suppose that we haven't seen it yet. And I should say that this is the option that in the end I'm going to be talking about for the rest of the talk. And that's just because to do effective field theory for Lepton Flavour violation, I need my new physics to be heavy. Okay, so if I have a mediator mass that is above the weak scale, then what you do is tune your new physics so that the Lepton Flavour violating coefficients that would arise at dimension 6 and 8 cancel in all the tree level amplitudes. And this has been also studied in some detail by various authors. And there are examples of how it works that so far succeed, as far as I know, to avoid constraints from the LHC. Okay. So I think I'm going faster than I expected, and it's going to be a short talk. So that was the end of the summary about NSI. There are also studies of NSI in astrophysics and cosmology, but I didn't look them up again before I gave the talk, so I didn't write a slide about them, and because I don't remember exactly what the punchline is. So here is a non-standard neutrino interaction again, and remember that for the purposes of finding them in long baseline neutrino oscillation studies, we would like this little dimensionless coefficient to be bigger than about 10 to the minus 3. And for that to be consistent with charged Lepton Flavour violation, you need to arrange some combinations of the epsilons to vanish, because charged Lepton Flavour violation bounds in the tau sector tend to give constraints of order, the sums of epsilons are 10 to the minus 4 or 10 to the minus 3. And in the muon sector, it's of order 10 to the minus 6. Okay, but will always be a particular sum of the coefficients. And so you can arrange to still have NSI. Now, I have to say, I personally don't like NSI. So I always have this dream that I should be able to kill them with charged lepton flavor violation. So the contortions one has to go through to make a heavy model avoid the tree level charged lepton flavor violation bounds might lead you to wonder, well, what about loop-induced lepton flavor violation? And so that was the purpose of what we did about a year ago. So we're assuming the NSI come from heavy new physics. We're neglecting the probably better motivated light Z prime impersonations. The reason we're doing this is because it allows us to do effective field theory, and, or in other words, to get a model-independent calculation of the log-enhanced part of loop diagrams. Now, as a parenthesis, let me add that, you know, obviously any loop diagram also has a finite part. And we could also get the finite parts in effective field theory, but the calculation becomes a lot more difficult. In other words, you have to calculate the loops. You have to calculate 2 loops to get finite pieces of 1 loop diagrams in EFT. So we didn't do that. And the only thing we can discuss is the log enhanced parts. And that means I can only talk about making the log enhanced part of the loops vanish. There might be finite pieces who don't vanish, but I don't know what they are. Anyway, with this assumption that new physics is heavy, we build a complete set of dimension 6 and 8 operators that are vector currents, they're standard model gauge invariant, and they either give lepton flavor violation or NSI. And then we suppose that every linear combination of coefficients of these operators that gives low energy lepton flavor violation is going to be 0. Decorate the operators with Higgs and W loops and check to see if now we get non-zero lepton flavor violating amplitudes that could be interesting. Okay, so let's start by doing an example. And this example has been in the literature for a long time. So we have heavy new physics, and we build SU2 invariant operators that represent it below the scale M. And I'm going to assume this heavy new physics talks to singlet right-handed neutrinos and to the doublets, okay? And that the only operator it is able to generate is this dimension 8 curiosity, where, remember, we contracted the lepton doublets with the Higgs via the antisymmetric epsilon. So this epsilon here, who is not curly, is the sigma 2 of SU2, right? No, it's I times sigma 2. It's the antisymmetric contraction. And if you decorate this thing, which is represented by this little gray bubble here, with W loops as indicated around the sides of the slide, or a Higgs loop, as here. You see there are two things you can do with the Higgs legs. You can close them and attach 2 more Higgs legs, or you can close them and insert a Higgs mass grid. Turns out all the W diagrams cancel, but these 2 operators will, so this diagram changes the index contractions on this operator here, such that at low energy, instead of getting NSI, you get LFV. And obviously, if you insert the mass in the Higgs loop, you get a dimension 6 operator, and there it is. It also gives you Lepton Flavour violation. So we got Lepton Flavour violation. It just so happens, however, that the coefficients of these two operators arise in exactly the combination that vanishes at the minimum of the Higgs potential. And you can sort of see that, right? Because you look at the two diagrams and, well, there's a mass squared inserted on this loop, and there's the Higgs to the 4 on that one. So for a long time in the literature, there was a little bit sort of folklore to hope that maybe if you canceled the Lepton Flavour violation at tree level, it didn't arise at one loop. So the reason we were sort of trying to do this very generic study where you put all the operators and allow arbitrary coefficients is we wanted to know, what about the other non-standard neutrino interaction operators? And also, what about higher order loop diagrams? Okay, so to do a more generic study, you need a complete set of operators. Now, if you have singlet external fermions, so this is our first generation fermions who, via the matter effect, or who become the density in the matter effect. And in the operators I've written down here, they are the right-handed electron. In that case, we've already seen the 3 possible operators you can write down in our basis. There's the one that gives NSI at only NSI at low energy. There's the one that gives only Lepton Flavour violation at low energy, who's called H2. And there's the dimension 6 one that gives both. And then if you allow your first generation fermion to be a doublet, you get a zoo of other operators and you get other diagrams, and it becomes a little more complicated. But the story remains the same, so I'm not going to focus on this. I'm going to stay with this example where we're making NSI on first generation right-handed electrons. And so here they still are, the same operators. And now what do we want to do with them is first match them onto our low energy theory and check that if we put that there are 2 ways to avoid tree level NSI. One is to just put the non-standard neutrino interaction. The other is you can put this guy who gives only LFV, and this one who gives NSI and LFV, and arrange their coefficients to cancel. And of course, somehow or another, we do want to get NSI, so we need either this non-zero or one of these non-zero. And then we calculate our loop diagrams, and you can show from our simple 1 loop diagrams that the log squared enhanced part of the 2 loop diagrams will generate Lepton Flavour violation from the NSI operator. But the suppression factor is 2 loops, so it's of order 10 to the minus 4. Whereas if you generated NSI by putting these 2 operators and engineering a cancellation between them, then you will necessarily get Lepton Flavour violation at 1 loop. So what it's telling you is that in the case of building NSI on singlet right-handed neutrinos, you are always going to get Lepton Flavour violation. And depending on how you do it, which operators your model gives which coefficients for, it will be suppressed with respect to the epsilon coefficient of non-standard interactions by 2 or 4 orders of magnitude. Now, we have a plot. Let me skip the plot because all it does is tell you the same thing, except it takes, I think it's a little bit confusing to explain. And think about whether those bounds are restrictive. Okay, so what for the SU2 singlet external fermions, as we just saw, we got LFV at 1 or 2 loop. Now, parenthetically, what you show for the, if their external fermions are doublets, sometimes you are able to arrange the coefficients to also cancel the 1 loop LFV, but it's again the case that you necessarily get Lepton Flavour violation at the log squared 2 loop level. So you are in generic always this situation where you get Lepton Flavour violation at 10 to the minus 4 to 10 to the minus 2 of the magnitude of your NSI. So let me use this relation to translate it into bounds on flavor changing NSI. So I have 2 tables depending on which end of this range I'm at. If I say that LFV is suppressed by 2 loops, then the table is the one on the left here. And so the epsilons on electrons are the first column. Sorry, electrons are the top column with mu to E flavor change. U's are the second column, second row. Downs are the last row. So you see that for mu to E flavor change, you already probably can exclude NSI due to heavy new physics, because you have a constraint that is of order 10 to the minus 3. Except for mu to E, and mu to E will improve, hopefully. The bound on epsilon will improve by an order of magnitude, or the sensitivity to epsilon will improve by an order of magnitude in coming years. Now, if it's a 1 loop effect, then the sensitivities are given in the right table. And you see that, again, as expected, NSI that change mu to E are probably inconsistent with Lepton Flavour violation. But again, the tau to E or tau to mu would be allowed. And unfortunately, for Lepton Flavour violation, fortunately for NSI, it's difficult to improve the sensitivity to Lepton Flavour violating tau decays. So I think I'm done. And I let you read the summary on your own, if that's okay.
Yeah, thank you very much, Sacha, for an interesting talk. So we have time for questions. We have plenty of time for questions. Who wants to go first? Maybe I start with one question. So you looked at Lepton Flavour relation, or the constraints from Lepton Flavour relation on those NSI operators. Could you also get something from lepton non-universality? For example, tau decays going there? Or is it basically because you were focusing on couplings to electrons that you don't have that?
So we only did the flavor violation because it's formally simpler.
Mm-hmm.
Just in building effective field theories, because as I'm sure you know, if you build flavor, you add flavor diagonal operators to the standard model, they interfere with standard model, the standard model Fermi interaction, Higgs exchange, whatever at low energy. So you have to put some effort into making sure you correctly defined G Fermi, for instance, in your formalism, to represent the standard model value so that when you do calculations, you're constraining the new physics. And we didn't want to implement that formalism in what we were doing. So we focused on the flavor change where you just parachute in your operators and their new physics. The other point is that we were focused on the loop-induced effects, and that means your lepton flavor violating constraint has to be restrictive in order to have a hope to say something about NSI, right? You're losing at least 2 orders of magnitude in the epsilon, and that means you need a constraint that is 4 orders of magnitude better. And you do have that in, for instance, mu-to-E flavor changing processes. You don't have it in the tau. Yeah. And I think universality violation, again, you don't have it.
Sure,
right?
It's like typically more like 10 to minus 4 or so.
It's a universality violation. You can put new physics just above the weak scale, as we see in the B in the B sector, right? So we didn't think about it. Now, on the other hand, it's an interesting question because it would be interesting to rummage in the literature and see if someone has checked that kind of constraint on NSI at tree level. Right?
True, where you don't have the loop suppression.
Forget the loop suppression and just check if you, after you've done these contortions to turn off the tree level LFV, are you consistent with universality violation constraints? Now, I think, for instance, from my memory of hearing Yasmin Farzan talk, that she does worry about that kind of thing with her light Z primes, for instance.
Okay, but that makes sense. Thanks. Are there other questions?
So I have a question.
Yes, so, go ahead.
Thanks for the very clear talk, Sacha. Just on the slide where you first introduce the W and the Higgs loops.
Yes.
Did I understand correctly that you said that essentially the sum of all of the diagrams with a W loop vanish? Is that right? The sum vanishes.
Yes.
So that's kind of surprising to me. Is there an easy way of seeing why that's the case, or it just falls out?
Okay, so it's only the case when the external fermions are singlets. Okay. But it turns out to be gauge dependent. In other words, you compute each loop. Each loop turns out to give you a contribution that's proportional to psi if you're working in arc psi gauge. And I don't know if it's related to vector current conservation. possibly. Because what will happen when you put the doublets on all the fermion legs is that the W diagrams will give you the usual loop contributions of, for instance, a photon for fermion operators. The same diagrams will survive. So it is almost as if the W doesn't want to see the Higgs legs, and it just counts what the fermion legs are doing, and it sees the fermions as being in vector currents that are conserved.
Okay, that's interesting.
But the short answer to your question is no, I don't understand.
Okay, but it's just for the case where you have the isosinglet electrons.
Right, it's the case where you are
Right.
You're exchanging between the fermions who are in a vector current or the Higgses who are mixed up with them in the same vector current.
Okay. Thanks.
Other questions?
I have a question.
Yes, please.
Yeah. So, Sacha, thank you first of all for the nice talk. Very informative for me, at least. And so you try to avoid this cosmological implication, but can you tell us whether these Lepton Flavour violating interactions or operators are relevant for, say, leptogenesis, or where I can,
Very good question. Probably yes. So if I'm trying to sell Lepton Flavour violation, I would say that it's a complementary window on the new physics of the neutrino sector, and that should you see it, you learn that the lepton sector is definitely, the mass generation mechanism in the lepton sector is definitely different from the quark sector. However, so that's the sales talk. Now, there's a parenthesis, which is that if you see Lepton Flavour violation, you probably did kill the, sort of canonical thermal leptogenesis in the type 1 seesaw. Because thermal leptogenesis in the type 1 seesaw works for right-handed neutrinos that are heavy. And if right-handed neutrinos, if you make neutrino masses with heavy right-handed neutrinos, you won't see Lepton Flavour violation at low energy unless you have other, you do in SUSY, but that's because you have other low energy Lepton Flavour violating interactions of leptons. So yes, if one were to see Lepton Flavour violation, this would be a lot of fun, because it would be telling you that you probably can do leptogenesis. In fact, you can do leptogenesis, but you would be doing it at some sort of intermediate scale, not the high scale gut version. So yes, interesting question. Thank you.
Thank you.
Further questions? let me ask another one. So in your work, you focused mostly on those right-handed, so singlet charged leptons or electrons, and then up quarks and down quarks. Do you have an idea what changes with if you would have doublets there? So in case of lepton doublets, or what was the reason to focus on the singlets?
It's just because, so so we're looking at the right slide now. This is the right-handed neutrino slide, right? You see, you get one constraint to avoid tree-level Lepton Flavour violation, and one direction that gives you NSI. So you're sort of living in a three-dimensional parameter space. You kill one direction, and now you're in 2D and you can make plots, and it is kind of intuitive. If I put an external lepton doublet, I think I only get one more operator, because, as I'm sure you are familiar with, if instead of putting the right-handed guy, you put the left-handed guy, you then have possible rearrangements, Fierz rearrangements of the four fermions that make some operators identical, right? So there's only one more operator, and it becomes more or less, it's still more or less manageable. You have one more dimension in your parameter space. When you put the quark doublets here, then you just start getting many more conditions. First of all, there will be a Lepton Flavour violating operator on the ups and a Lepton Flavour violating operator on the down at tree level. So you have two constraints. And so instead of just having these two nice equations, I would be writing 6 or 7 or something, and it starts, in a talk at least, it starts to become confusing, at least for me. But it's in the paper.
Okay, good. So that makes sense. That makes sense. That makes sense. That there are many more constraints and many more things to take into account. Other questions? I don't see any at the moment. So let's thank Sacha once more for a nice talk and good overview about what's kind of this charged Lepton Flavour relation and whether one can see NSIs or not in neutrino oscillation experiments. If you want to ask more questions, I'm sure that Sacha will stay connected for a little bit longer to answer more, but let's thank Sacha. First of all, for a very nice talk. Yeah, so thanks a lot.